Okay, it's very nice to be here and to open the second week or the second whole week of this school. I'm going to be talking about conformal invariance or conformal field theory and statistical mechanics, which is a subject which has been around since the 1980s, but it's still a very important subject, and I think the sort of things that I'll be talking about are things that every theoretical physicist should somehow have an idea of. Anyway, so I've got 5 items here. I'm not quite sure whether these are the 5 lectures, but more or less I'll be talking today about basic ideas of scale invariance at a critical point and how this gets promoted to conformal covariance, and I'll talk about some very simple consequences. Then I'll go on to talk about the Gaussian model, which is basically a free scalar field theory in which we see quite a lot of these ideas realized. In the third lecture, or roughly the third lecture, it'll become a little bit more technical. I'll talk about the role of the stress tensor, the Heresero algebra, its representation theory, and how this occurs in what are called the minimal CFTs. I'll change gear then in number 4. I'll go back to the lattice and I'll give you explicit examples of lattice models whose scaling limit corresponds to the minimal CFTs. It turns out that these lattice models are best realized in terms of not the local degrees of freedom, but in terms of random curves. And then in the last talk, assuming I get there, I want to talk about a mathematical theory which helps us to describe the probability distribution of these random curves, which is called SLE. And I hope I will get to the point where I can show how SLE links back to CFT. So we will see how it goes. So I encourage you to ask questions, of course, and I'll try to pitch this at a level which I hope most of you will actually understand, but if you don't, if I'm not being clear, please do ask questions either in the lecture or in the tutorial section or generally afterwards. Okay, so I'm going to start off by talking about the scaling limits of lattice models. So the prototype lattice model is, of course, the Ising model. So just to remind you what that is, we take a lattice, a d-dimensional lattice, a lattice in RD, in d-dimensional Euclidean space. I'll almost always be working in d-dimensional Euclidean space. So here's a lattice. Of course, on the blackboard, I can only draw the case d equals 2, but you can imagine some d-dimensional hypercubic lattice. And the sites of this lattice are labeled by R. R is a vector, but I won't always put the vector notation on it. And then at each site of this lattice, we have an icing degree of freedom, S of R, that can take the values plus or minus 1. Okay, and this model is defined by its Boltzmann weights. So each configuration, S of R, has a weight which is proportional to e to the minus beta, sum over R and R prime, sum over sites on this lattice, some ferromagnetic interaction, some, and that should be a plus in that case, S of R prime. So the main thing is this could be a nearest neighbor interaction, but it does not have to be. The main thing is that it's short range. That is, it goes to 0 over the scale of the lattice icing. And one thing that I didn't not introduce yet as a matter of notation, we denote the lattice spacing by A. Spacing we call A. Okay, so that's the model. And of course, if we want to work out the expectation value of any quantity, what we do is to take the trace, which means summing over all configurations of whatever we want to work out the expectation value of times the weight of that particular configuration divided by the partition function. Basic, standard, equilibrium, stat mech. Okay, so in general, in particular, if we look at the correlation function of two spins at the point R and the point R1 and R2 and subtract off the expectation value squared. So if we look at the connected part of the correlation function, in general, this thing as R1 minus R2 goes R1 minus R2 goes to infinity, decays exponentially with the correlation length. So this thing here is the correlation length. And this, in fact, defines the correlation length. So I'm now in a position to define what I mean by the scaling limit. The scaling limit is that we take the lattice spacing to 0. That is, on this picture here, we imagine taking some fixed region of the space and making the mesh size finer and finer, okay? Finer and finer. So A goes to 0, but keeping the correlation length fixed and keeping all the other distances fixed here. R fixed. If we're working within a finite region here, D, we also keep that fixed. Okay, so that's the scaling limit. And one thing to observe about it immediately is that if you think about the correlation length as measured in units of the lattice spacing, so all these things here have dimensions of length, okay, then, but if we measure the correlation length in units of the lattice spacing, that's some intrinsic property of the lattice model. So in general, this thing is of order 1, but the model has a critical point, and when we go close to the critical point, the correlation length as measured in units of the lattice spacing diverges. In fact, it goes like beta minus whatever the critical value of beta is to the minus nu, where nu is a critical exponent. In the case of the two-dimensional Ising model, we know this critical exponent is 1, but in general, it is some irrational number. But this tells you that if we're going to take A goes to 0, keeping the correlation fixed, this has to go to infinity. So therefore, beta has to approach beta critical in a certain way as a power law in A. So it's important to realize that the scaling limit, which is what I'm going to be talking about, is only going to apply to the lattice model either at the critical point where the correlation length is infinite or close to the critical point. So all the universal properties, which are properties of the scaling limit, only apply to the lattice model in that region. Okay. So most of the time, I'm actually going to be taking the correlation length to be infinite. That means that I'm going to actually be working at the critical point. So you can then ask, if I take the scaling limit, what happens to correlation functions? Okay. Well, in general, they are not actually finite. So even though we keep the correlation length finite, R1 minus R2 finite, the number outside here is not finite. Okay. So in order to obtain something finite, what we have to do is something called renormalization. That is, we have to renormalize the lattice degrees of freedom. So in the case of the spin-spin correlation function, if this actually diverges as we take A go to 0, or rather it becomes singular. It doesn't have a finite limit, but if we multiply by a suitable power of A, which is 2 minus xs, for a suitable xs, then the limit as A goes to 0 of this power times the lattice correlation function, so this is a lattice correlation function, exists. And the xs depends on which particular model we're looking at, what particular universality class we're looking at. It depends on what particular observable we're actually studying. In the case of the two-dimensional Ising model, when we look at the spin-spin correlation function, it happens to be equal to 1/8. 1/8, yes. So, but in general, this is a number to be determined, and part of the, yes, one moment, part of the thing that we're going to try to study is to try to extract what these numbers are. Yes, question? Oh, sure, yes, I thought I was, but yes, I will, certainly, yeah. Okay, So that's just one example of a correlation function, but more generally, we can define lattice observables that are called phi lattice J. Okay, J labels which observable we're talking about, which are sums of products of local spins of the SA. They're local. So one example is the energy density, the lattice energy density as a function of R, which is sum over R prime J of R minus R prime S of R S of R prime, exactly the object that occurs in the Hamiltonian here. So we have the spin, the energy density, and those are the ones that you usually talk about when you read a book about the two-dimensional Ising model. But in fact, there are an infinite number of local observables which you can make out of products, local products of spins and suitable linear combinations. The only important thing is that they have to be local. And so this index J is supposed to label all of those, this vast multi-dimensional space, okay? So in general, what the scaling limit says is that if we take a correlation function phi of J1 lattice of R1, phi of J2 lattice of R2, dot, 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 some endpoint function on the lattice, and we look at how this behaves in the scaling limit, then it has to be renormalized, but it has to, and the way to renormalize it is to multiply by a suitable power of a to the minus x J1, x J2, dot, dot, dot. So there is a suitable power of a for each of these lattice observables here. And then the idea is that the limit as a goes to 0 of this thing exists as long as you choose these numbers xj in the right way. So this limit exists, and we call it phi J1 of R1, phi J2 of R2, dot, dot, dot. This is the continuum limit of this lattice correlation function. So I've now dropped the superscript lattice here. So this is the scaling limit of a correlation function. And this function is a correlation function of a Euclidean quantum field theory, okay? Euclidean in the sense that we're working in RD, not in Minkowski space, D-dimensional QFT. So I'm not going to prove any of this. In fact, it's really hard to prove. In fact, what I'm saying here is the product of a consensus which has grown up over many, many years using ideas such as the renormalization group. This is what you get when you apply the renormalization group to these kind of models to exact solutions. And more recently, though, I should say, in the case of the two-dimensional Ising model, this has actually been proved. So it was proved in a series of papers by Stanislav Smirnov and his collaborators. And for that work, he received the Fields Medal. So you can tell how hard it must be to actually prove this, okay? So I'm not going to prove it. We are going to take this as read that the scaling limit of these lattice models exists, and we are going to explore the consequences of this limit existing and try to understand what the properties of this limit must be. Okay, so one consequence of the existence of this limit here is that these objects themselves are scale covariant. That is, if I look at phi of J1 of B of R1, that is, I rescale all the distances now by a factor B, phi J2 B of R2 dot 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 is equal to B to the minus xJ1 minus xJ2 dot 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 of phi of J1 of R1, phi of J2 of R2 dot dot dot. So I leave it to you as an exercise to actually, and maybe it's something that we can discuss in the tutorial, to show that the fact that this limit exists and the fact that on the lattice things only depend on R over A, okay, because on the lattice doesn't know what units we are using to measure distances. It doesn't know whether we're using centimeters or inches or whatever. Okay, so this correlation function only depends upon R over A. The fact that this limit exists implies that the continuum limit, the scaling limit correlation functions, when we make a scale transformation, okay, of the distances, is not invariant, but it behaves covariantly. That is, it just gets multiplied by a suitable factor of B. So one consequence of this, well, one other thing that I should mention about the scaling limit is that if we start with a lattice model which is isotropic, for example, on a square lattice, if the interactions in the x direction are the same as the interactions in the y direction, so it definitely has a symmetry under 90-degree rotations, then that gets, in the scaling limit, that symmetry gets lifted to full rotational invariance. So I'm going to assume or assert that the scaling limit is also rotationally invariant. So one consequence of this is that if, for example, we look at, if we go back to the two-point function, phi of R1, phi of R2, but now in the scaling limit, then we have that phi I of B of R1, phi J of B of R2 is equal to B to the minus xi minus xj. So I look at the correlation function of phi I and phi j times phi I of R1, phi j of R2. Okay, so and because of translational invariance, this is a function only of R1 minus R2, and rotational invariance, it's therefore a function only of the distance. And this scale covariance then tells you that the 2-point function phi I of R1, phi j of R2 is proportional to 1 over the distance R1 minus R2 to the xi plus xj. Okay, so it tells you that 2-point functions decay as a power at the critical point. So I said way back, I said that away from that in general things decay exponentially, but at the critical point the correlation length is infinite, and this exponential decay is replaced by a power law. And so this shows you how these numbers get related to the well-known critical exponents, which you can read about in any book on critical behavior. Okay, so any questions so far? Okay, so now I'm going to talk about how this scale covariance gets lifted, gets enlarged to conformal covariance. So we have this equation here, and I'll call this equation star because it's a very important equation. Not that one, sorry, the other one here. The one below it that I boxed, this one here. Okay, so it tells me how a correlation function transforms under a scale transformation. Okay, so the idea is, and I'll present to you the heuristic hand-waving argument, that we started with a model which had local interactions. We assumed that the Hamiltonian was local. So maybe there should be some generalization of this equation to the case where B is not a constant, but is smoothly varying in space. So we are going to make B go to a smoothly varying function of R and ask whether there might be a similar sort of equation. Okay, so if we do that, then it's no longer going to be true that R is going to go into B times R. It's going to go into some function of R. So R is going to go into R prime, which is some function of R. Once again, these are vectors, okay, in d-dimensional dimensional space. So it's one small step for a human, but a huge step for humankind to generalize this to the following equation: phi j of R1 prime, phi j2 of R2 prime is equal to the product is equal to some number which I'm going to call j of r1 to the minus xj1, j of r2 to the minus xj2, dot, 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 times phi j1 of r1, phi j2 of r2, dot, dot, dot. So the idea is under this transformation, this correlation function is going to transform covariantly. And what are these things that I've called J? They are going to be nothing but the Jacobian. J of R is going to be the Jacobian of the transformation R goes to R prime, which we can write symbolically like this. Now, so we're going to postulate an equation like this. Now, this can't be true in general. It can't be true for a general coordinate transformation. This would be too strong a result because it would actually imply that all correlations had to be constant. You can easily see this. So if this was true for any coordinate transformation, the only solution would be that all correlation functions are constant. This is actually what happens in what's called a topological field theory, but we want to not talk about a topological field theory, but a conformal field theory. So my argument was based on trying to lift this covariance under scale transformations to something larger. So what we're going to say instead is that this transformation is equivalent locally to a scale transformation or a possible rotation. So is locally a scale transformation plus a scale transformation plus a local rotation. So that doesn't include all possible coordinate transformations, as we will see. So so transformations of the plane or R to the D that satisfy this are called conformal. So they are conformal if they are locally, they look like a scale transformation and a possible rotation. So just to give you an example of what I mean, if this is a system of coordinates, so it's now not a lattice, it's just a coordinate grid, okay, which is R. And I'm going to map this into R prime, and I'm going to draw the lines of constant Rx and R prime x. So if this is x prime and y prime, and this is xy, I'm going to draw in the original plane the lines of constant x prime and y prime. And they're going to look something like this. For example, this would be an example of a conformal mapping, which is locally a scale transformation where I stretch things, but you notice that the amount of the scale transformation depends on where we are. But locally, So locally it's a scale transformation and a rotation, and the important property of a conformal mapping is that it preserves angles. You see that this remains a square grid here. All these angles remain square. So a conformal mapping also preserves angles. So you can think of the set of conformal transformations as those that locally preserve angles. So this equation here is going to be the generalization of the one we wrote over there to conformal transformations. So I've only motivated this heuristically. We may or may not get to the point where we can see why it's true in a more systematic way. It turns out that it's true in theories that have a local energy momentum tensor, a local stress tensor, which includes all relativistic quantum field theories, all rotationally invariant Euclidean quantum field theories with local interactions. But once again, this is one of these results which was actually proved to be true for the two-dimensional Ising model, and we can show that it's also true for other models that we can. Okay, well, I will give you. If you don't mind, I'm going to wait on that, and we'll see how that goes. Although I could explain it now, and then I won't have to explain it again. Okay? So this is the topic of conformal mappings. Okay, so the question was, how do we know a given mapping R goes to R prime is conformal? Well, one way to look at it is to think about a mapping which is infinitesimally close to the identity, right? Where we only make a small change. So if we look at an infinitesimal one, so R goes to R prime, which is R plus alpha of R. So alpha is going to be some infinitesimally small function of R. I could put an epsilon in front of it if you want, just to remind us that it's very, very small. Okay, and I'm going to start using coordinates now, and I'll put the coordinates upstairs just like we do in GR, okay? Because as long as we're just using Euclidean coordinates, it doesn't matter whether we use upstairs notation or downstairs, but there will be a case where we are going to want to actually distinguish. So mu runs from 1 up to D. Okay, so if we want to know what this transformation is doing locally, what we do is to work out the derivative of this function. So we call it alpha mu comma nu, okay? So this is a d by d tensor, okay? It's got two labels, and we can break it up. So altogether there are d squared entries here, okay? But we can break this up into an anti-symmetric part. Sorry, draw it last. Okay, this is anti-symmetric. We can look at the part which is proportional to the trace, alpha mu, alpha lambda summed over lambda delta mu nu. So this is antisymmetric. This is proportional to, this is diagonal. And then the other pieces which I haven't written, I'll put 1/2 there, is the symmetric traceless part. And so there's something like a 1 over d, this thing here. Okay. So I can always decompose this rotational tensor into an anti-symmetric part, which is going to correspond to a local rotation, to a diagonal part, which is going to correspond to a local scale transformation, and the rest. And the rest is really the components of this tensor which correspond to shear. Shear like this. Okay, so you can think of this thing as labeling, you can think of alpha of r as labeling the positions of particles in some elastic medium, right? And so what we're doing here is nothing but working out the strain tensor. Strain tensor of an elastic medium, and we can say that it's a linear combination of a local rotation, scale transformation, a shear transformation. So the idea of a transformation which is locally conformal is that it just has these components and not this. So we have the requirement that there should be no local shear, so that the symmetric traceless part of this tensor has to be 0 for the transformation to be conformal. I think that answers your question. Now, I'm not going to go through the solution of this, but what you can maybe see is that as we increase the number of dimensions, these constraints increase. Okay, because there's only one component here, there's a small number here, but this is of order d squared. So there are order d squared conditions here, and they become harder and harder to satisfy as you keep increasing d. So what actually happens is that it all depends on whether d is equal to 2 or whether it's bigger than 2. So the set of conformal mappings for d larger than 2 is somewhat restricted. So let me first mention these. So for d bigger than 2, we of course have the usual group, the usual symmetry group that we assumed was the property of the scaling limit. It was translationally, so we have translations. We have rotations. And we have scale transformations, which are sometimes called dilatations. So we have these. So what do we get extra? Well, it turns out that there's really only one component, one extra thing that we get, which is which are called inversions. So an inversion is when r prime mu is equal to r mu over r squared. Okay, so in order to get an inversion, what we do is to draw a sphere of unit radius at some origin. We can choose it doesn't, because we have translational invariance, I don't have to do this about the origin, but that's what I've chosen to here. And this basically maps, so when I have a point here which is on some radius going away from the origin, and this distance is rho, it maps it to a point out here where this distance is 1 over rho. So it's this inversion about a sphere, and you can easily check that it's just a nice exercise in Euclidean geometry to prove that this preserves angles. Okay, so this, of course, is not an infinitesimal transformation. It's a finite one. It takes things a long way away from where they started. So the way to get an infinitesimal transformation out of this is to start by doing an inversion, then do an infinitesimal translation by whatever amount you want, and then invert back again. You will end up with a point here somewhere. So this point, if this is infinitesimal, this is infinitesimal, and that's how you can generate an infinitesimal conformal transformation. Okay. So, but basically, the whole set of conformal transformations in J dimensions is generated by these, plus this extra operation of inversion. Okay, so the fact that you have an extra symmetry tells you more information. So we said the fact that we had scale invariance, translational invariance, and rotational invariance, this told us the form of the two-point function, minus x1 plus x2. Okay. These three things told us this. Now we have one extra element, and it tells us more things, right? Once you have more symmetry, you know more things. And in fact, this extra thing tells us the form of the three-point function. So phi1 of R1, phi2 of R2, phi3 of R3 goes like, and I'll write it down, it's a bit complicated. You can see it's going to be complicated, all right? So it's R1 minus R2 to the x1 plus x2 minus x3, R2 minus R3 to the, okay, it's cyclically invariant. So once you know one of these terms, you can write down the rest. x3 plus x1 minus x2. Okay, so using this additional symmetry allows you to do this. And basically, it's because the reason that we could use these three things to get this result was that we could use the first three to map any 2 points, R1, R2, into any two pre-assigned points, for example, 0 and 1. Okay, so we can use these transformations to map 2 points into 2 pre-assigned points. When you add this extra operation of inversion, if you have 3 points, you can then map them into 3 pre-assigned points. For example, 0, 1, and 2. Though in the books, they usually do it to 0, 1, and infinity. In terms of conformal field theory, infinity is a perfectly good point, and but you can think of it as 0, 1, and 2 if you want. So this extra operation of inversion allows you to actually do this. And I'm not going to give this as an exercise because it's one of these things where there's an easy way of doing it and there's a hard way. And the hard way is the one that you would probably first try, and you will get into excruciating algebra. But all you basically do is to use this equation here for 3 fields here, get the map, work out the mapping that sends these 3 points into these 3 pre-assigned points, work out all the Jacobians, and these 3 pre-assigned points, it's just a constant. So everything is in the Jacobian. So it's just a matter of working out these Jacobians. Now, there's one more thing to say here. It only gives this 3-point function up to a constant of proportionality. And if we normalize the fields such that if I take these indices the same, this is 1. This is the conventional normalization. I can choose to normalize these any way that I want, but I normalize them such that it's 1. And then this is not 1, it's a number, which I'll call C123, C12FT. Yeah. Oh no, it occurs in D equals 2. Oh, sorry, yeah. Phi 1, Phi 2, Phi 3. Different fields. Okay, so it's really phi of J1, phi of J2, phi of J3. Okay, so they and this one, these will be x of J1, x of J2, x of J3. No, these don't have to be the same field. What I'm saying is that for any choice of phi of J1, phi of J2, phi of J3, the form of this 3-point function is this, where these x's are the x's of each of these fields, okay? And then there's a number upstairs, which just depends on which fields we have chosen. So it's CJ1, CJ2, CJ3. They're all normalized in the same way. Yes, so phi J1, phi J. Okay. Yeah, okay. So actually, there is another consequence, which I think I can erase here, which is actually, if you take 2 different fields here, that is, if I take phi of J1, the 2-point functions, phi J1, phi J2 of R2, just the 2-point functions of 2 different fields, it's actually proportional to a delta function. So if I take the 2-point function of 2 different fields, it's 0. Okay, so R1 minus R2, it doesn't matter which one I choose. So this is another consequence of this inversion symmetry. So going back to our two-dimensional Ising model, well, that's a bad example, so I won't give it. Okay, so I'll stop there. Okay, so you have this kind of orthogonality here, that the two-point functions form a kind of inner product between the different scaling fields, such that the two-point function is proportional to the delta function. That's also important. Okay, so yes, I started late, so I can finish late, right? Okay, so now something special happens in D equals 2. So let me just erase this here. So D equals 2 is special because there are many more conformal mappings. And the way to see this is to use what are called complex coordinates. So we had our Euclidean coordinates R1 and R2, or X and Y if you prefer. If we define in the usual way a complex number, Z, which is R1 plus I R2, and Z bar is R1 minus I R2, then we can use Z and Z bar as complex coordinates, And of course, they're not independent in the sense that Z bar is the complex conjugate of Z. But in fact, most of the equations make sense if we ignore the fact that Z bar is the complex conjugate of Z. Just think of Z and Z bar as being linearly independent, which of course they are in the complex sense, right? Okay, so the point is that any analytic function Z goes to Z prime is f of Z such that f prime of Z is non-zero corresponds locally to a conformal mapping. And you can see that if you look at the derivative and think of that as being, and writing this in polar coordinates, rho e to the I chi or something, so that rho is the modulus of f prime and chi is the argument of f prime, then this just corresponds to a local scale transformation. This just corresponds to a local rotation and nothing else. There is no component of shear. So any analytic function is locally conformal. So that means that rather than just having just a few more operations that we can do, because we could think about expanding this locally analytic function in a Taylor series, the local conformal transformation will be parameterized by the coefficients of that expansion. So it's an infinite dimensional symmetry. And as I told you before, the more symmetry we have, the more we can say, the more constraints we have. This means that in 2 dimensions, the constraints of conformal symmetry are much stronger, and for that reason, most of what I'm going to be talking about in this course is going to be strictly in 2 dimensions. So, sorry. Because of this, right? So this is no, this is not the infinitesimal part. This is a whole thing. So it actually becomes singular if the derivative is 0. That will become obvious in what I'm just about to write down. So there's a generalization of this equation here, or sorry, not a generalization, but a sort of specialization, that phi j1 of z1 bar, phi 2 of z2 bar, dot, 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 and this is prime, is equal to f prime of, actually, yeah, 1 over f prime of z1 to the minus delta j1 f prime of z2. Let me just write this down and I'll explain it in a moment. Okay, so I've rewritten this equation here using complex coordinates. So instead of R1 prime, I've got C1 prime, C1 bar prime. Instead of R, I've got C1 bar. But these Jacobians here, so if you take, so I've introduced these numbers here, which are delta and delta bar. And these are the complex versions of what I call the scaling dimensions x, A4. So if this number delta is the same as this number delta bar, then this term combines with this one to make the modulus of f prime, which is just her Jacobian. So xj is delta j plus delta j bar is scaling dimension. And if we were just talking about scalar operators, that is just talking about scalar fields, ones which were rotationally invariant, that's all that we have. But we can also look at the difference of delta minus delta bar, call it Sj, call it sigma j, is delta j minus delta j bar. This is called the conformal spin. So in general, in a two-dimensional theory, each field comes associated with these two numbers, delta and delta bar. And the sum of them tells you how things transform under scale transformations, because that involves the modulus of f prime, and the difference tells you how it transforms under rotations. And it's called the conformal spin, though you shouldn't confuse it with quantum mechanical spin. It just is, we're not doing quantum mechanics here, we're doing Euclidean quantum field theory, even though I keep calling these operators, I shouldn't yet, they're really just fields. So also the notation here is a bit confusing. Although C bar was the complex conjugate of Z, delta bar is not necessarily the complex conjugate of delta. In fact, these quantities are usually real numbers, distinct real numbers. Okay, so let's see, complex coordinates. So let's see. What I'd like to do is to do a little calculation now, which is an example of an application of this mapping here. Okay, so we're going to look at a particular conformal transformation which is going to tell us about correlation functions on the cylinder. So I'm going to start in the plane, in the complex plane, which is r squared. So z is going to be a coordinate in this plane, or z bar. Okay. And I'm going to choose a particular analytic function, which is capital L over 2 pi log of C. Okay, the logarithmic transformation. So this is going to be what I'm calling C prime. Okay. Sorry, I don't know how that prime got there, but yes. No prime. Thank you. So you see, if I write Z is R e to the I theta, then C prime, which I'm going to also call U plus IV, is going to be L over 2 pi log rho plus L over 2 pi times I theta. So if I think about the whole of the Z plane here, here's the origin, this is rho, this is theta. This gets mapped into an infinitely long cylinder, which I can't draw, so here's a cylinder, but it's supposed to be infinitely long in the, and this is U, this is V. U is going along the cylinder, V is going around the cylinder, okay? As theta goes from 0 to 2 pi, V goes from 0 to L, so the circumference of this cylinder is L. And the origin gets mapped into minus infinity here, plus infinity gets mapped into plus infinity here. And we can then use this equation here to get the correlation functions on the cylinder as functions of U and V in terms of correlation functions in the plane. So I'm just going to look at the 2-point function. which it does here. So I'm only going to look at a theory which has no discontinuity, at fields which have no monodromy as I go around here, right? No discontinuity. I can generalize it to, for example, something which will look like a fermion where it changes sign as I go around here. That would mean that I have antiperiodic boundary conditions here, and that's certainly something which is an interesting generalization of what I'm going to write down, but I'm not going to have that here. Okay. So we can write down, so let's just choose a general field phi, and we write it as C1 prime, C1 prime bar, phi2, C2 prime, C2 prime bar. This is going to be on the cylinder, is going to be, and I'm going to assume it's scalar. So x is going to be delta plus delta bar, which is going to be 2 delta. Okay, so I have d c1 prime by dc1 to the minus x1, d c2 prime by dc2 to the minus x2 times the same correlation function, but in the plane, in R2. But this, we know what this is. This is just the modulus of C1 minus C2 to the 2x. Okay, so here's an equation. We can easily do it. I won't necessarily go through all the algebra. Okay. In fact, I think in the interest of time, I won't go through the algebra at all. But I hope that you can see that we have this, that we know this equation here. We therefore know c as a function of c prime. It's e to the 2 pi c prime over L. So we can plug this thing into here. We can plug it into the Jacobian and then just do the algebra. So I'm just going to write down the result. I'm afraid I'm not like Professor Redner, who goes through all the algebra on the board in front of you. I'm going to trust you that you can go away and actually do it yourselves. Otherwise, you trust me that I've done it right, okay? So this is 2 pi over L to the 2x divided by 2 cosh 2 pi u1 minus u2 over L minus 2 cosine 2 pi v1, sorry, v1 minus v2 over L. And this thing all gets raised to the power x. So this is phi on the cylinder. So you see a few things here. First of all, if we think about distances which are much, much smaller than the circumference. So if u1 minus u2 and v1 minus v2 is much, much less than L, then I can expand out this hyperbolic cosine and this real cosine, and I get 1 minus this thing squared, I get 2 minus this thing squared, minus 2 minus this thing squared, and you can check that what you get is 1 over u1 minus u2 squared plus v1 minus v2 squared, all raised to the power x, which is 1 over mod C1 prime to the C2 prime to the 2x. So at short distances, much less than the size of the cylinder, we get the same answer that we did in the plane. Okay, which is what we would expect, but it's a good check of our calculation. However, if we take here's U1 and V1 and here's U2 and V2, we can take U1 minus U2 a long way, we can take the points a long way apart. So now if U1 minus U2 is much, much bigger than L, what do we get there? Well, this number here is getting large, and the hyperbolic cosine of x when x gets large is just basically e to the x, or e to the x over 2, but there's another 2 here. So this is blowing up exponentially. But it's 1 over this, and this term is also going to be much larger than the cosine term, which is bounded by 1. So what we're going to find in that limit is a phi of u1, phi of u2, and I won't even bother to insert the dependence on v. It's 2 pi over L to the x, e to the minus 2 pi, e to the minus 2 pi x, modulus of u1 minus u2 over L. So it's decaying exponentially. So I said, well, wait a minute, you might say, I thought you said that correlation functions decay exponentially away from a critical point. Well, that's exactly what is happening here, because this cylinder is quasi one-dimensional, okay? And if you know anything, for example, about the one-dimensional Ising model, the correlation functions always decay exponentially. There is no critical point in one dimension, so everything decays exponentially, and that's what we actually find. So things do decay exponentially with a correlation length, however, that depends upon which particular observable we are studying. And the inverse correlation length is this thing here, which is 2 pi x over L. Okay, so things are decaying exponentially as though we were not at a critical point, but we can see that we actually are, because this is proportional to 1 over L, 1 over the size, 1 over the width of the strip. As we take the strip bigger and bigger, L goes to infinity, this goes to 0, so the correlation length is actually still infinite. And the fact that it goes like 1 over L is an example of what's called finite size scaling. Okay, so if we were not at the critical point, the correlation length in the strip would depend on both L and the true correlation length in the infinite system. But the true correlation length in the infinite system in the plane is infinite, so that doesn't come in. And the only length scale in the problem is L, so it has to be proportional to 1 over L. This is what's called finite size scaling. But the interesting thing is that the amplitude here depends on the critical exponent. So this is actually a very useful relation, because it gives us a way of numerically extracting critical exponents in a very efficient way. And I'm just going to finish by explaining that. So let's suppose we now have our cylinder, try to draw it. And we now put our lattice on there again. Okay, so here's our lattice. So here's our icing model, but now defined on the cylinder. And notice I draw the square lattice on the cylinder. I don't draw the conformally transformed lattice. That wouldn't be doing anything. But I'm doing something by looking at the square lattice on the cylinder. Now, how many of you know about the transfer matrix in statistical mechanics? Okay, so you can think of building up the partition function on the cylinder by having a matrix which I call T, which takes us from one row to the next row here, or one column rather, to the next column. And its rows and columns are labeled by the values of the spins along here. I call them S, and the spins along here. So I can build up the partition function by multiplying the transfer matrix by itself many, many times. And I can build up the correlation functions in the same way. So, for example, if I've got my U1 here and my U2 here, then I can compute this correlation function in terms of a transfer matrix where I start over here at minus infinity, and then I have to start in what's called the ground state, or the state corresponding to the largest eigenvalue of the transfer matrix, times phi times the transfer matrix acts from here to here, so raised to the power U1 minus U2 over A, where A is the lattice spacing by ground state. So I can compute correlation functions on the cylinder in terms of knowing matrix elements of the transfer matrix between certain states. Now, usually we write the transfer matrix as e to the minus a times h, and h is essentially, in the scaling limit, becomes the Hamiltonian of our conformal field theory, which generates infinitesimal time translation. So the transfer matrix is the exponential of the time translation operator h over a distance of the order of 1 lattice spacing. Now, if I insert in here a complete set of eigenstates of my Hamiltonian, let me call these energies En, then I can write this as sum over n phi 0 phi hat n times e to the minus u1 minus u2 times En. Okay, almost finished. Times n phi hat 0. So you see, by inserting a complete set of eigenstates of my Hamiltonian, or equivalently of my transfer matrix, I can read off the exponential decays as u1 minus u2 goes to infinity. And if I compare it with my result over here, or this exponential decay, we see that En is 2 pi x over L. So this is a bad notation. It tells us that for each scaling operator phi with a scaling dimension x, there corresponds an eigenstate of the transfer matrix, or equivalently the Hamiltonian, with an energy which is given by this formula here. Now, I've cheated a little bit. It should be the gap. So it should be the energy of the excited states above the ground state, because here I've assumed that the ground state has zero energy. So this is an example of a fundamental result, that there's a one-to-one correspondence between the scaling fields phi j and the eigenstates of H. H, which is equal to minus 1 over A times the logarithm of the transfer matrix. So by numerically diagonalizing the transfer matrix, which, as long as you have a finite number of lattice spacings here, is relatively easy to do, you can read off the scaling dimensions of all the scaling fields in the areas. So this gives you an extremely powerful way of numerically understanding things. So just one more remark. What I will hopefully show later is that you can not only get the gaps, but you can actually get the ground state energy, which is related to what's called the conformal anomaly number of the conformal field theory, which is something I'll explain probably on Wednesday by pi c over 6L. So you can not only extract all the scaling dimensions numerically, you can also extract the value of C. Okay, I'll stop there. Any questions, please? I guess we have time for one or two now, and then, yeah. Yes, right. Yeah, yes, so what we do is that we diagonalize the transfer matrix for different values of L. We plot these gaps versus 1 over L, and the slope is given by this. Okay, well, we do have parallel decay at short distances. We have exponential decay because the system is quasi one-dimensional. Okay, for any finite L, for U1 minus U2 much bigger than L, we have exponential decay. But if we fix U1 minus U2 and take L goes to infinity, so it's much bigger than the other way around, then we have a parallel decay. Okay? Yeah. Yeah. Yes, that's a good example. I mean, I was trying to give an example in the icing model where you take one of the operators to be the spin and the other to be the energy density, but that is, the 2-point function of that is 0 because I can change the sign of all the spins. But if I take the energy density and I take a suitable linear combination of the product of 4 spins. Now, that's what I said, that when you take these lattice operators, you've got to take suitable linear combinations of them, so I get a pure power law JK of the 2-point function. So otherwise they're not scaling fields. So there is some particular combination of the product of 4 spins minus the sum over the 2 spins. And that particular combination you would have to calculate what it is, such that the 2-point function of that thing decays with a pure power law. And then if you take the correlation function of that with the energy density, then it's 0. In the scaling limit, it's not 0 on the lattice,